In this part of lecture, or we consider that few lectures following this one, we will go for digital electronics, which is little different from our discussions what we made in diode circuits, where the analog signals were used, and finally at the end we went for diodes to use for digital logic gates, which will be used in this part, but later. In this lecture, I will discuss about digital electronic and in its the number system which we use in the digital systems or number systems in digital system. We basically will discuss about the number system today. Now, since I am talking about digital system, so in the digital system basically we talk about the binary systems and its evolvement in different manners, so that our digital computers, they understand the language what we want to convey to the system, so that it respond as per our requirement. So, it is as if like starting from our conventional thing and then giving a link of that to the digital computer, which only understands switch on and off, none other than that. Since I am talking about digital computer, which is a electrical device or electronic device in which we have only option, either I will ask to flow the current or I will not ask to flow there, or only potential will be there, present there of non-zero value or zero value, or some higher value or lower value, only these two states. So, by considering that idea, we will represent the numbers which we generally consider in such a way that computer understands. Okay. So, we are talking about those numbers or number systems which will be understandable by our computer, but we never forget about the physical happening or the things which we see in physical domain. Just like say any number n 25.375, so this is a number. This is an absolute one numerical value where 25.375 we call. Just like say pressure somewhere is of this much amount, or temperature somewhere is of this much amount. This way we understand, but computer cannot. So, to make the computer understand, let us discuss about few number systems which computer will able to understand. Is the first decimal, then binary, third is octal, and fourth is hexadecimal. These are the number systems we use in computer, where this decimal number, if you have some idea that this is directly to the physical happening where the numerical values are there involved, present, and those are presented in some other manner. Let us see which way. So, let us come first with the number which is given in this fashion to us, that may be pressure, temperature, whatever I said there. Now, I would like to explain this number in different manner. Just like say, since I am seeing here some point is there, then there might be difference between this part and this part, because one is before this, another is after this. Let me take this part which is in front of it, say 25. Let me divide it by 10. If I divide it, it is not directly divisible, but some remainder part will be there. So, how much maximum? It is found it is 2, but some remainder is there. How much it is? 5. Beyond that, would I able to divide it? It is not possible. Okay. So, if it has come in this fashion where this 10 is involved, So let me see this, that I want to represent is one number here which is given here as 2, 5. That is nothing but 2 and 5, where maybe somewhere 10 is involved. Okay. Similarly, since this complete is a number, complete thing is a number in which after this point this quantity is slightly different. So let me take that part 0.375 and multiply it with 10. I can do, because this 10 is used here, so I am taking again the 10 there. If I do so, how much it is coming? 3.75. But in that I am saying one part has gone beyond the point which I demarcated with some concept there, that something is there in that point. So that front part and later part is taken in different manner. So let me take this 3 as carry somewhere. This 3 as a carry. If I take that carry, who is remaining there? 7.5, 0.75. Now again I will multiply it with same 10, the 10 what I considered earlier. So it will become 7.5. Again I do the same analysis. 7 is carry. Again I will be taking the remaining part 0.5 there into 10 equals to 5.0. Carry is 5. Then who is remaining? 0 into 10 equals to 0. Nobody is there as carry there, 0. So I have done this way. Now with this I want to represent one number there where I will take these remainders in this fashion. I am following that notation actually. I will take this notation in this fashion, up. Starting from here, I will be going here. If it would be more than this, then I would go from the bottom to top. Then I will be representing them. Okay. Similarly, here these which have come there as carry, I will be taking them from bottom to top, top to bottom there. What is the meaning here I am trying to convey? I want to say, I want to represent this number in such a way that these remainders will be coming there using them, and the carries which have come there using them, I will be defining a number. How can I define? I am seeing here, since it was divisible by 2 with remainder 5 there, then this quantity may become like this, 2 into 10 plus 1 5 is there found, with which if I multiply 10 to the power of 0, then I am close to this value, 2 into 10 plus 5 into 10 plus, I am regularizing the thing, plus this quantity 3 into, again in terms of 10 if I am talking about, then I will represent it as 10 to the power of minus 1. It is possible by noticing this arrangement here what we have made, the way we found 3, 7, 5 or 2 and 5 there. From there only we can make the observation and write an expression for a particular number there like this, so that I can write 7 into 10 to the power of minus 2 plus 5 into 10 to the power of minus 3. Okay. So the number, this one which is represented here n in this fashion, it is coming exactly same with this convention where the remainders will be there. I will be going from this side to up, and carries which will be there from top to bottom. Do I need to take this 0? I can take 0 into 10 to the power of minus 4 like that, but it is multiplied with 0, that is why I have not taken, but you can extend it. Okay. Now if it is represented this way, then let me express this expression in this fashion. Here I am saying everywhere for each and every quantity 10 is there as a multiplier, maybe sometime 10 to the power of something positive, 10 to the power of negative or 0, like that. So, let me name that 10 as R. That means all are represented in terms of R, which is say called base of it, which is a base from where remaining things will be generated in terms of which. Okay. Now, I am seeing that with this base, something is getting powered of starting from 0, plus 1, minus 1, minus 1, minus 2, minus 3, like this. Even it can go for higher numbers in positive side and in the negative side. Now, look into this one. It is a coefficient which is multiplied with this R base, which is varying from place to place, where each and every place 0 is there with some power, 10 is there with some power there. Let them name as say d of n here, where this n is power here, which is here coincidentally 1. So, I will call this 2 as d1. Similarly, this as d0 and this as d minus 1, because I am seeing here r to the power of minus n means minus 1 it is there. So, that way these coefficients are named as d and base is named as r, and all have there some power of 10 there or base there n value. So, it is represented in this fashion. So, can I say this number n I am representing in this fashion dn r to the power of n plus dn minus 1 r to the power of n minus 1, same thing, up to which d1 r to the power of 1 plus d0 r to the power of 0 plus d minus 1 r to the power minus 1 up to a higher value. Let me complete like this. Okay. Now, this is the generalized expression what I have presented here. From this, I have put this r and this d to make the expression generalized, so that a number n I can represent in terms of d and r and n, small n. Okay. Now, if this equation is with you and from there you are deriving this one, where you are putting r as 10, where n can be any value and d also can be of any value, but r is same for all. So, the number what you have represented here, that is in terms of 10. Okay. So, this number will be called a decimal number, where base will be 10. Okay. Now, whatever the number system we will be talking about today, you will see those should always follow this generalized expression with some base r there. Let us check throughout this lecture and till end. So, I will be keeping this equation here itself and I will be rubbing the remaining part there. One small observation before I leave this part. If I say I have taken r value 10, for which I have got this number here, where the n is represented as decimal number. What are the possibilities of the remainders or the carries? What are the possible values for remainders or the carries? From 0 to 9. Since you are taking r equals to 10, it has only option that this d values will run from 1 to up to 9. That means 10 possibilities are there. So, these d values should be within that. Now, how many numbers will be there, that decides how bigger the n values, how many bigger small n value it decides that how long your number is or how bigger the number it is given to you for representing in say decimal system, decimal number system. Okay. Now, if I want to represent it in another number system where r will be taken not 10 but 2. Let us try the same thing. Procedure will be exactly same what we considered there, and we will proceed. Let us try. Okay, let us take the same number divided by 2, because you are saying you will take now r equals to 2 there. So, 12, remainder is 1, again 2, remainder is 0, 2, remainder is 0, 2, remainder is 1. Two, 1, 1. What is that? 12, 6, 3, 2, 1. No, it should be 0. This is 12, remainder is 1, 6, remainder is 0, 3, remainder is 0, 3, 1, remainder is 1. Yes, fine. Now, as we have taken the notation there, we will be going up like this while representing. If it is so, then the number might be coming in this fashion 1, 1, 0, 0, 1, 1, done. What is about the next part? After point, because I have taken 25 just before that point. Now, let us take that one also, 0.375 into 2, how much it is? 0.75, carry 0, then 0.75 into 2, 1.5, carry is 1, 0.5 into 2, 1.0, carry is 1, again take 0, okay. So, now if it is the carry, so I will be going top to bottom. So, I will put one point here. Since this point was there, then I will be representing them from top to bottom. If you want to put 0, put it. Okay. Now, in this, why it came only 0 and 1, not 1, 2, 3, 4 like this? Because you are talking r equals to 2. So, how much remainder it can come? Either 0 or 1 only. So, it has come 0 and 1. Simple logic. Okay. So, now since you have taken 2 here, so if this is the number n which you are now representing, then the system number system is with r equals to 2. So, this is the binary number, where bi term is indicating that only either 0 and or 1 there. Okay. So, this is the popular binary number what you have already come across with. How to make the decimal number to binary or binary to decimal. What you did in the binary to decimal conversion? You took the value here and multiplied with some value. It is actually this one. But still, let me write the thing in decimal. Like if I take, this is the number given to me. Now, let me identify the n values. Where is the small n equals to 0? I think this is the part just before the point. Here n is equals to 0. Then what is 1? Plus 1 here, minus 1 here. Okay. So, if I represent it in this fashion where I am saying 1, 2, 3, 4, here it has come n 4, just like this. So, what is d4? 1 into r to the power of n. This is what you wrote. Okay. Similarly, again the coefficient is 1 multiplied with r with n value n minus 1, then 0 into 2 to the power of minus 2, then 0 2 to the power of minus 1 plus 1 into 2 to the power of 0. Four, 3, 2, 1 and then 0 plus 0 into 2 to the power of minus 1. I am just writing this one. 1 into 2 to the power of minus 2 plus 1 into 2 to the power of 3 plus 0 if you want to put. Simply I will write down n as how much it is? 16 plus 8 plus 1 plus 0.5. No, it is 0. 0.25 plus 0.125. So, it is from where you started? Anything? It's fine. Okay. So, up to this I consider that we knew from earlier. Okay. So, this is the concept which is there with us. Again we will be using this repeatedly. Maybe for octal or hexadecimal we will be taking a few more discussion on this, but before I come to that I will go for another thing here where the sign numbers are also to be considered there, because it could be plus minus 25 plus 25.375 or minus 25.375, but our computers doesn't know what is the sense of plus or minus. If it is plus 3 or it is minus 3, how does it know? So, to make that understand, we have to do something somewhere so that computer can understand, yes, this is plus 3 or this is minus 3. I have to say which way. So, then there also I have to develop some technique so that I will be following some way, which way I will be converting one plus 3 or minus 3 into digital form, and computer also understand that. Okay. So, for that let us see which of the sign numbers are represented. Say I have taken this way, side by side I will be comparing them. Say I have plus 3 here or plus 2, plus 1 like this, that I have to represent in binary form so that my computer understand. Okay. So, tell me what is 3, 1, 1, 2 to the 2 divided 3 is divided by 2, remainder is 1, 1 and 1, the same technique. Okay. So, 1 and 1. Now, if I say this is only 3, what is about plus sign? So, let us consider that if it is plus to be represented, put a 0 for it. If it is minus, put 1 in front of it. Say it is 3, 1, 1 it is written there. Now, since I am saying it is plus 3, let me put one 0 here. If it is 0, it is a positive number. If it is 1, it is a negative number. Okay. Now, if I take a 4-bit system where I will be representing the numbers by not 3 bits, but say 4 bits. In that case, I can put another 0 here in front of it, still the number is 3. Now, my question goes that which one is the bit for representing the sign, positive or negative? In that case, either you consider 3 or you consider 4, that does not matter. The number what you represent here in the binary system, the MSB or most significant bit is for sign. Fine, this is the convention. It is 4, 5, 6, does not matter. The most significant bit MSB will be always representing the sign there. Okay. Now, if I ask you 2, how much it will be? 1, 0, here it is 0 and again 0, 1, 1. Fine. Now, tell me about 0. How will you represent? 0, 0, 0. What is about the MSB? Why? I can put 1 also. What is the concept of plus 0 or minus 0? 0 is 0. Okay. So, let me take their 0. Let me take. This positive is in 0 side, say basically 0 we cannot define. Slightly higher than 0 or lower than 0, but still say 0 it is there. Now, how to represent negative signs like minus 3, plus 3 is there. Now, I want to represent minus 3. In that case, one concept is there, 1s complement implementation, where they say that if you take complement of the sign bit, it is automatically going negative, but that does not work always. But if you take 1s complement there, you have to take 1s complement for all. What does it mean 1s complement? Make zeros to 1 and 1s to 0, just inversion. So, that 0 the sign bit become negative, positive to negative or negative to positive. Okay. Now, say plus 3 was like this. If I take this concept, minus 3 should be 1, 1, 0, 0. Now, since it is MSB is 1, so it is a negative number, but it is a 3 here for negative. After you take 1s complement, your term has given you the negative value of 3, but that is not like simply making it 1. It have to make inversion for all, so that it will represent you minus 3 now. Similarly, for minus 2 if you want to represent, you take plus 2 and take its 1s complement, just this one, 1, 1, 0, 1, this for plus 2, oh sorry, minus 2, minus 1, 1, 1, 0. This is for minus 1, minus 2, minus 3. Now, if I take 1's complement of 0, if I take 1's complement of 0, it will become 1, 1, 1, 1. I can take if the number is available there with me. So, this is actually negative 0, where earlier you took positive 0. So, in 1's complement notation or implementation technique, if you want to represent the negative, positive numbers and negative numbers together, you will see there one concept will be coming there of positive and negative number, which is really confusing. Okay. So, this way people prefer to use this implementation for represent negative number, but better one you can consider where this concept will not be there, where implement is 0 which is coming together there. If you just simply go for some one small increment, like you take the 1's complement of this and add with it. So, in that case you will not face this kind of problem. What is it? Just see. Oh sorry, 2's complement. 2's complement straightforward says that 1's complement plus 1 at LSB means least significant bit. That means, if you represent plus 3 in this form, minus 3 should be represented as plus 3 if it is 0, 0, 1, 1. In that case, minus 3 should be represented in this fashion, that first you take 1's complement of this 1, 1, 0, 0, then you add with 1 at the LSB. So, it become 1, 0, 1, 1. Okay. Now, it is minus 3, since it is minus, this MSB has come 1. So, there is a sign bit basically, and the remaining are representative for the numerical number 3 there. I think this is quite different from this one. Okay. So, now if you want to get really the number which you have converted there, to get that one, after you get this number, you got the MSB, so it is 1, so it is a negative number. Now, you take 1's complement of it, then again add with 2. That means, you take 2's complement of this one. If you take 2's complement of this, how much it is coming? 0, 1, 0, then 1, again it is 0, 1, 1, 3, that means 3. So, the idea is that after you know the sign of it, again the remaining part you take 2's complement of it, it will give you the actual number from where you started, which is quite different from the other. Okay. Not only that, this 2's complement, where 1's complement and 2's complement both are used for representing the negative numbers, but 2's complement has another advantage, that it does not require any subtraction operation. Only by doing addition operation, it can make the subtraction also. How? If a negative number is given to you, you take its 2's complement and then add. So, it will give you the actual subtraction. Why do I prefer this? Because if you go for simple subtraction of binary numbers, you need to borrow some values, where you have only 2 options, 0 and 1, which become little complicated for subtraction, which is not at all there if you go for 2's complement representation for a negative number and add that negative number after you make 2's complement of it and proceed. Which way? Let us take the example. say I ask you this number, do subtraction of 22 with 17. Simply you write down the binary expression for 22 and 17. Please quickly. How much? 1, 1, no, 1, 0, 1, 0, 1, 1, 0. Is it like this? 16 plus 4 plus 2. Is it fine? 22. See here, if you represent this 22, here how many bits are there? 3, 4, 5. But generally in our digital systems, we like to represent the number in terms of 2 to the power of some value, just 2 to the power of 0 or 2 to the power of 1, 2 to the power of 2, like that. Means either by 1 bit or 2 bit or 4 bit or 8 bit, like that. Okay. So now since it has gone for 5, let me take 2 to the power of 3, because 2 to the power of 4 is already exhausted. So let us go for 2 to the power of 3, that means 8 bits. So 3 more bits let me incorporate, so that it does not disturb the actual number, simply to make it 8 bit, nothing else. So 22 is represented in this fashion, where this part is the 22 and remaining 3 zeros at the left hand side, 0 into 2 to the power of something, 0 into 2 to the power of something, which is coming here, useless. Okay. Now I need to do the subtraction here. To do so, first I will write 17, this number, in binary form. How much it is? 16, 0, 0, 1. 1, 0001. Yes. 2 to the power of 3. 2 to the power of 3 means 8 plus 2 to the power of 0, 1. Fine. How many bits are there? 5. 1, 1, 1. If it is plus 17, then this might be minus 17, because I have taken 2's complement of plus 17 as this. So if I add this with the other one, that means if I take 1, 1, 1, 0, 1, 2, 3, 4, after that I have to simply add, nothing else, because already this is a negative number. Take the addition, 1, 0, 1, 1, 1, 1, 1 and 1 means 1, 0. This is overflown. So you take only 0, but still 1 is there. So you carry it, 1, 1, 1, 0, again another 1, 1, 1, 1, 0, 1, 1, 0, 0, again 0, 0, 1. How many bits? So this, if it is 9, then this is overflown to this. Okay. You have started with 8 bit. You can handle only 8 bit data, nothing else. Okay. Now if I ask you, what is the sign of this number? It should be positive, because the MSB is 0. Okay. So if it is positive number, I do not have to take any other action. Only thing is that I will see what is the number is coming here. Obviously it is plus 5, but I will ask you revert one. If I go for minus 22 plus 17, it should come minus, it should come minus 5 as a result. Please do it. How much? I think I will take this number this is plus 22, it was. So, I will take 1 1 1 0 1 0 0 1, then again 1 1 1 0 0 1 0 1 0 1 1 1. Fine. Here 1 0 0 0 1 plus 17 minus 22 is fine. Plus 22 was like this, then inversion of it, then 1 add. Is it fine? Please check it. Zero. Is it coming fine? Then give me the final expression. I think it is coming all 1. I got like this. Why it is like this? 0 0 0 1. No. 0 1 0 1 0 1 0. 17 is fine. 17 is 0 1. Oh, I wrote 1 bit less. Huh? Now it is fine. In this case, 1 2 3 4. 1 2 3. Another 4 is supposed to come there. Fine. Is it fine? So 8 bits are there. 8 bits are there. If it is so, this MSB, it is 1. So it is negative. If it is negative, take 2s complement of this one. If you take 2s complement of it, it's supposed to come 5 with negative sign because of this MSB. Okay. So this way you proceed for negative signs there.